everybody. I hope everybody's having a wonderful day. So let us get started here. So just remember last day we were talking about binary search. So we're doing some time complexity analysis. And I stopped at the point where I was deriving a complexity function for us to analyze. Now, I came up with this recurrence relation. So a recurrence relation in our context is just simply a function that is written in terms of itself. So I have t of n is equal to t of n minus 1 over 2, where that's the input to my function here, plus 1. So this is when there is more than one element. And when there's none, I have one step. So the 0 represents when the range, the interval crosses, or it is when, so that's our t of 0 is equal to 1. This plus 1 is a non-recursive work. So remember, we talked about how when we analyze the recursive algorithm, what we do is we break it into two pieces, the non-recursive work and then the recursive work. So the non-recursive work is I simply analyze this algorithm under the assumption that these recursive calls, they just take constant time. So I just treat them like if they're an elementary operation. I don't count them. And then what I do is once I've counted up that non-recursive work, under the assumption I just pretend these just aren't invoked. Then what I do is I look at what each of these recursive calls look like. I determine how many recursive calls are happening and how big are those on those recursive calls with respect to the input size. So you'll notice that in binary search, we have it where we have one recursive call that happens. So if it doesn't find the key, it either discards one half of the array or the other half, the left half or the right half. So remember, that's what we call binary search, so you're bisecting the array. So the thing I want you to notice is that we always discard one half or the other half along with the middle element, one that we check to see if we have a position. Now I want to give you a quick intuition of where this n minus 1 over 2 came from. So this is a simplifying assumption I'm making. And I wanted to elaborate because you might possibly have watched the last video and were like, okay, well, he went a little fast and didn't explain that very much. So I'm going to give a concrete explanation just with a picture because I think it helps a little bit. So I have an array here and it has n elements in it. So when I consider the middle position, because remember, you agree with me that binary search never, when I do the recursive calls, never checks the middle position. Now remember, that's just one element in my range. I don't really care where it is, so I'm just going to stick it over here. So in reality, it should be somewhere around here. But I just want to keep track of how many elements I'm actually going to take into account when I do the recursive call. So, because this is basically mid right here. Remember, mid would actually be somewhere about the middle, but I'm just counting how many elements would I have to consider in my recursive case each time I do a recursive call. So remember, every time I throw away a half. Okay, so what's a half now when you look at this? Well, it's right about here, right? So how many elements do I have right here? Well, I discard the middle one. So this is exactly n minus 1 elements. And if I cut that in half, that's where n minus 1 over 2 comes from. So all I'm assuming is that whenever I do this, I can get it so it cleanly divides n minus 1 over 2. This is just to prevent me from having to deal with the cases where I round down it. It makes it a little bit easier to play around with when I assume that it's at least this, because this is the nice case. So hopefully that clarifies where this comes from. So I want you to imagine when I do my recursive call, I'm going back to binary search here, because I just want to explain this carefully. Okay, so I perform this. So imagine I give you n as the length of the interval. And remember, the length of interval is the number of elements. I discard one of them, and then I consider half of those, at least, right? I know more than half of them are going to get considered. That's why we're okay with this assumption. So if I were to look at this one, you'd agree with me that basically this range is completely dependent on the length of the array in terms of the range's length. So when you look at n here, you shouldn't be looking at, hey, look, that's the whole length of the array. You should look at this as the current interval for which we're looking at. That's how you should look at this recurrence relation. So this recursive call is really just a calculation of how many elements I have being looked at so far. Okay? So when I break this down, when I discard a half or another half, it relates to the interval, not the entire array. It only does when we start. Hopefully that's clear. So just like in our example where I was throwing away halves of the array, I don't literally do that in the algorithm. I just only consider the part for which I don't throw away, right? And that's what this recursive work is representing. This is that recursive call right here. So I'm just looking at this range. How long is this? Well, it's u minus, it's based on the relationship between u and lowercase l, or fancy l. Okay? So now what I'm going to do is I'm going to analyze this recurrence relation. So I need to do something with this. I'm going to do something we call solving a recurrence relation. Now, the one thing that's a little bit confusing when people hear the word solve in this context, they literally think I'm like solving an equation. What I'm actually doing is I'm coming up with a nice formula that represents the recurrence relation without the recursive parts. So I just want a nice little formula, a closed form, that represents what the recurrence relation is doing. That's what I mean by solve. Now, we're going to do this more loosely, where we're going to have big O in play and also. So we're just going to care that we can get a good idea of what the recurrence relation is doing. But I'm going to be very particular and careful here, okay? So let us solve T of n by repeated substitution. We're going to use a technique called repeated substitution. So before I get to that, just remember big picture. I'm going to come up with a nice formula that doesn't have this T of n business in it. That's just going to represent the total amount of work that's being done. And I'm just going to simplify that over there. So that's actually like a formula I can play around with that I can classify in terms of big O. This isn't particularly useful in this stage. It's very intuitive because it's a recursive algorithm, but we want to really know what's happening in terms of big O. So that is, we will try to find a pattern by expanding the recursive part of the recurrence. And I'm going to do this by writing each as a new equation. You're going to find that the way I do this is going to be almost like if you were to imagine that piece of the array every time I consider it, that interval, if I'm almost simulating this process as I perform and create each one of these new equations. So naturally, you're going to find that I'm going to try to eventually bring this down to where the base case occurs. So I'm going to change this period into a comma because I'm edgy like that. I know radical stuff. So until we reach the base case. So there's the game plan. So don't let this sound a little too daunting. It's going to look complicated if you don't pay attention. So follow me very closely here. So I'm just going to start off by writing T of n is equal to T of n minus 1 over 2 plus 1. That's what it is. That's what I have over here, right? Now remember, the base case is T of 0. You want to get down to t of 0. Remember, t of 0 represents when the intervals cross, when L and U cross. Now, what I'm going to do is I'm going to now create another equation where I consider this one right here. And I'm going to keep performing this repeated substitution. So I'm going to write another equation where I'm going to place this right here. I'm going to write another equation that represents that recursive part of this equation. Okay, so now remember, don't let this get a little too intimidating. So you see that it says n minus 1 over 2 here. That's the parameter that's being fed to the function here. Before it was n, now it is n minus 1 over 2. So don't let this look too scary. So if you're having difficulties imagining what I'm seeing, imagine n is an apple. Now, n is now an apple here. So it's t of apple is equal to t of apple minus 1 over 2. So keep in mind, the apple is still this one right here. It isn't this whole part here. So when I go and write it down over here, when I write everywhere where I see n in my original right here, I will literally write this, which maybe I'll call it banana. This is a banana. And I'm going to write the banana. Remember, that's now what n is, because now n, the input, is n minus 1 over 2. Minus 1 over 2 plus 1, right? That's what that is. So all I've done is I've just placed in the input where it belongs by its definition. Now all I'm going to do is I'm going to simplify this a little bit, see if I can find a pattern. So this is just t of n minus 1 minus 2 over 2 squared. Notice that I have this extra 2 kicking around and that I can factor nicely. I'll let you think about it and try calculating it out yourself, which I end up with t of n minus 2 to the 0 minus 2 to the 1 all over 2 squared plus 1. So when I write this out and I simplify, you'll notice that, okay, well, you see that I really just have this extra 2 kicking around. So I've just made a common denominator here by including an extra 2. And then you'll notice that, hey, look, this 1 here, that really just looks like 2 to the power of 0. I'm just going to try to find a pattern here, just using my pattern-seeking ability. If you're doing this more formally, you would actually try to prove that this formula is a thing, but that's going to be beyond the scope of this course. So now all I'm going to do is I'm just going to put that right over here, this recursive part from over there that I simplified over here. Remember, don't let it look complicated. Remember, all I'm doing is, this is the input. I'm going to write this input where it belongs over here by substituting it by its definition. And then I'm going to simplify again and see if my pattern continues. You're going to see that there's going to be something involving powers of 2, just like over here. So don't let this look too complicated. Remember, all I'm doing is I substitute in n, and then I perform a simplification. Then I insert the recursive part of this over here, and then I simplify. I'm going to do the same thing where I'm just going to put this over there, and I'm just going to see what it means when I substitute that in. So what does this mean? So this is t of n minus 2 to the 0 minus 2 to the 1 minus 2 squared. So if you simplify this, you'll get this right here. I'll let you check it. So if you perform some simplifications, you should end up with t of n minus 2 to the power 0 minus 2 to the power 1 minus 2 squared all over 2 to the power 3 plus 1 outside of there. You can keep doing this. So if I keep writing down these equations, I'll get a nice general form. So eventually I'll get a pattern kind of going on where I can really see it. I'll end up with t of n minus 2 to the power of 0 minus 2 to the power 1 minus all the way until I get to 2 to the power of some j. over 2 to the power of j plus 1. Does everybody see that? So notice that the pattern goes, every time it goes up by, it always introduce another power of 2, and the power of 2 in the denominator always goes up by 1 higher. Do you see that? So what's this? Well, I can just write this again. Well, this is just t of n minus 2 to the power 0, 2 to the power 1, all the way till 2 to the power of j plus 1. J plus 1 all over 2 to the j plus 2 plus 1. But I want you to observe something that's interesting. As I keep doing this over and over again, the input value given to t decreases with each equation. So I'll say the input value given to t on the left-hand side decreases with each new equation. Now, when do we stop doing this? I want you to think about this. When do we stop doing this? Remember, I said that ultimately we want to get to the base case. What's the base case? That's t of 0, right? We stop this process when we reach t of 0, right? Now, you might naturally ask, okay, well, why are these two powers keep popping up? It's because, remember, every time you kind of halve everything, and it's going to allude to the running time of this algorithm, because it looks like we have a bunch of exponentials being applied every single time I'm halving things, which in the running time, in our way we're doing our analysis, it looks like I'm taking away exponential amounts by increasing powers. We're going to find out that's going to be the inverse of our running time. I don't want to spoil it too much. I'm getting excited just thinking about it. I can't contain myself. So I'm just going to take my pattern over here, this one right here. I want to know when this is actually equal to 0. So imagine there's some point where this thing is going to equal this, but this is going to become t of 0, this whole thing here. So that means that the number here has to become 0, this result inside the input here of t. So 2 to the power 1 all the way to 2 to the power of j plus 1 all over 2 to the power of j plus 2 is equal to 0. So I want when this happens, right? I want to get to t of 0. So that brings me to something interesting. Let's think about this. Then t of n is going to be equal to a whole bunch of things. It's going to be equal to 1 plus 1 plus 1. These are all going to be my plus 1s that I had in each one of these equations. So notice I had this plus 1 here, I had a plus 1 there, I had a plus 1 here, and I had a plus 1 there. All of these have a plus 1 associated with them. I want to know how many of these occur. Because remember, each one of these would be, if I were to take this like an accordion, what I would do is I would scrunch these back together, and I would eventually get t of n again. So I just squeeze them together, and I get t of n. So this is if I'm spreading it out. Each one of those takes a constant number of steps, which I just marked as 1 step. I want to know how many of these happen. So I'm just going to put in this. So that's going to be basically what our closed form is going to come out of, is this thing. So I'm going to simplify this a little bit. And I want you to take notice of how many equations I wrote down here. Okay? Just carefully notice this. So this is just 1 plus 1 plus 1 plus all the way another plus until I get the t of 0 plus 1. Okay. So now if I look at this, how many equations did I write down? Okay. You can almost look at this one like, okay, that's 2 to the power 1, 2 squared. Then we got 2 to the j plus 1 here. But remember, I started off with t of n, right? But t of n, you can almost look at this like I didn't have any powers subtracted at all. And like if I divided by 2 to the power 0, right? So how many of these ones actually do exist? Well, the easy way to look at this is, okay, well, how many of these do I got? I got 2 to the power 1, 2 to the power 2 squared, 2 cubed, all the way to 2 to the j plus 1. And then I have 2 to the j plus 2 being the next substitution. But there's this 1 associated with that. How many 1s are there then? 2 to the j plus 2. Many. So I'll just write t of 0 off to the side here. But the big point is that there's j plus 2 many 1s. So just count up the number of times I substituted beyond this until I reach over here. And you'll notice that I have j plus 2 new equations once I put this guy in. Because I get this extra 1 from that, right? Because I really just care about having it where I reach t of 0. So you just got to imagine it like I'm doing the algorithm, and every time I do this halving process, I want to know how many times that happens. So now it's going to be related to this j variable that I have kicking around. That brings me to an interesting point now. I can write this more simply. And this is where things are going to get a little bit weird. But I assure you, they will be clear. So the whole point was to find a pattern, and notice that I was just increasing by powers of 2 every time. Well, this is t of n is equal to j plus 2 plus 1. Now what we're going to do is I'm going to mark a specific equation that I have. I have this one right here, right? I'm going to call this one star. This one where I have all these powers of 2 divided by another power of 2 is equal to 0. I'm going to star that equation. I'm going to use this. So we need to determine what j is. Because we don't know what j is. So to determine the value for j, we can use star. So now this is the great part, and this is going to be kind of strange at first. Okay, I have this very complicated looking thing. If I multiply by 2 to the power of j plus 2 on both sides of this, I can eliminate the left-hand side, but I also 0 times that is just going to be nothing, right? So I'm going to end up with this thing, just the numerator is equal to 0. So I'm just going to write that now. So I have n is equal to the following. Now here's the great part. Once I have it written like that, I can just add each one of these powers of 2 to the right-hand side. So I get a nice equation that relates n with all these powers and j. So I have 2 to the power 0 plus 2 to the power 1 plus all the way till we get 2 to the power of j plus 1. Is that neat? But what is this? What is this? I'm going to write this with the summation here. So this is I from I0. So I'm going to make a variable I that's going to represent each one of the powers of 2. So I start off at 0, and I go up to j plus 1 of 2 to the power of I. Well, that's interesting. Why is this interesting? I want you to think. You might know that this looks like it's particular finite series. So this is a finite geometric series. So in the formula, this is just with r is equal to 2. So I'm just going to apply that. So I end up with n is equal to the sum from I 0 to j plus 1 of 2 to the power of I, which is equal to, now I'm going to just apply the closed form for the geometric series. So just look up this series closed form. It's just 2 to the power of 0 minus 2 to the power of j plus 2 over 1 minus 2. So the 0, this is L, the lower limit, so 0. Then this right term is the upper limit plus 1. So j plus 1 is j plus 2. And I have 1 minus r is 2 here. If I simplify this, I get 2 to the j plus 2 minus 1. Now this is where the magic happens. This is not the mayonnaise word, the dreaded M word. This is truly a beautiful thing. So what I'm going to do now is, now I have this and that. So I have n related to a j. So what I'm going to do is I'm going to move the minus 1 to the left-hand side. Then apply logarithms to both sides. And so this is what I get. I do take logarithms to both sides. Like I said, you're going to see that this weirdly exponential thing is actually its inverse, which is logarithmic. But I don't want to spoil the full fun of this. Okay, so now, just to see what we're going to do, here we go. So I just take n is equal to this. Remember, I move the minus 1 to that side, so now it's n plus 1 is equal to 2 to the power of j plus 2. So I end up with log base 2. I'm just going to take log in terms of base 2. Makes sense. You'll see why. Is equal to log base 2 of 2 to the power of j plus 2. Now, if you know your logarithm rules, you can apply the power rule of logarithms, and you can pull this exponent out front and multiply it. So I can take this and write this as j plus 2 times log base 2 of 2. So this is using a power rule. So this is the power rule of logarithms that I'm using here. It's called the power rule. And now this is the great part. What's log base 2 of 2? I'll ask you a very simple question. Okay, so what exponent can I take to the power of 2 so I get back 2? 1, right? So this is just equal to j plus 2. Because that's just 1. This is 1 right here. That's 1. So now this is where it gets really lovely. Okay. So now I know that log base 2 of n plus 1 is equal to j plus 2. But what did I establish earlier? I told you that T of n was equal to j plus 2 plus 1, right? Well, T of n is equal to j plus 2 plus 1. And now I have j plus 2 is equal to this. So I just substitute in the j plus 2. which equals log base 2 of n plus 1 plus 1. And I'll let you check that this is log big O of log n. You can put the base 2 in if you like. And we're done. So that's how we could show that binary search takes worst case logarithmic time. Isn't that cool? So we use this interesting pattern that we got out of the recurrence relation by repeatedly substituting in the input of the recurrence relation to identify a pattern. Then we just simply added up all those ones that we got from each one of our equations. And we count up how many of those happened. And then all we did was we just tried to identify a pattern in relation to this J, which represents the number of real substitutions that are going to occur. Those substitutions correspond to our recursive calls, the number of times that happens. Isn't that neat? I love it when mathematics tends to be very intrinsic to how the algorithm behaves. So, lastly, I want to talk a little bit about space complexity for binary search. Because I haven't really done a proper example of space complexity, so thought I'd show you this. Now, I can't remember if I erased binary search or not. I may have. But remember in that algorithm, we don't use anything other than a constant number of variables each time. And I can assume that the array every time is being referenced. I'm not copying over the entire array every single time. So I'm passing it by reference, like a pointer. So notice that we use a constant number of variables. However, so if I were just doing things like this, notice I didn't use any extra, like I didn't create another array when I was doing things. So if I did anything like that, like it might account for the space complexity. However, notice I didn't do any of that. So where's the space complexity going to come from? It's going to come from those recursive calls, believe it or not. However, we perform recursive calls. Each creates an activation record. So remember, when we talk about the call stack, we talked about last class. An activation record and is placed on the call stack. Or just the stack. I'll just refer to it as the stack. Call stack. Call stack. How many recursive calls are made? So that's ultimately our question, and that's what will determine the space complexity binary search, at least this recursive version. So how many occurred? Remember, every time I made that recursive call, I put an activation record, which represents the parameters of and any variables I may use for that method or function call. And I noticed that each one has a constant number of variables, and each one obviously is finite size, and each one's constant size. So all I have to do is count up how many of these recursive calls, so how tall that call stack can possibly get. Now, this is the great part. We already actually did all the work for that. Do you see what I mean? We actually did all the work. We counted up how many recursive calls were happening in the worst case. What was that? That was big O of log n. So, big O of log n. Big O of log n calls in the worst case. So the call stack gets at most big O of log n high. in the worst case. So the space complexity in the worst case is big O of log n. And we're done. See, I put all the brunt of the work into us doing the analysis for the time complexity because it kind of gives us a space complexity for free. Now, I should make a couple of remarks. So you might naturally know, you're asking, well, Dan, why are you talking about the recursive version of binary search? There's actually a way you can write this algorithm without any recursion. And I think that you know what I'm talking about, possibly. If not, that's perfectly fine. I'll describe to you how you would do this without recursion. I'm not going to write anything down. So every single time I have those upper and lower limits, right? So I have L and U. What if I make a while loop that just updates U and L? So instead of doing a recursive call, I just simply update U and L. Just like I do with the recursive call, just replace the recursive call with updating L and U in my algorithm. And that's really all you have to do, which is quite interesting. So you just use a while loop. What would the space complexity be there? Well, I only have one activation record when I do this. So the worst case space complexity would just simply be big O of 1, which is great. So I'll just mention that note. Binary search be rewritten non-recursively so it uses a while loop and has space complexity. So I'll just say space complexity in the worst case, but I'll just write space complexity, big O of 1. So that's one thing you got to keep in mind is sometimes when you're doing these recursive algorithms, if you can get rid of, if you really are harboring on about space, maybe writing it iteratively might be able to take care of that, but that's not guaranteed, okay? Pretty often, though. So that brings me to kind of coming back to one major point. So, remember we talked about linear search and binary search. So let us compare linear search and binary search. I'll just abbreviate as BS. Just don't take that literally, okay? So let T1 of n and T2 of n be their complexity functions. So that, now I'm just going to write down, I'm going to go back to that set theoretic way of interpreting big O. So I'm just going to write these down so that T of 1 of n is big O of n, which this just simply equals T1 of n, such that T1 of n is less than or equal to C times n for all n greater or equal to n0, where constants C n0 this. This is just the definition of big O again. I wrote this the other day. And T2 of n is big O of log n, which equals T2 of n, such that T2 of n is less than or equal to C times log n for all n greater or equal to n0, where constants, again, c, which is a positive real constant, and we have n0, which is a positive integer constant. Okay, so these are my two. So imagine I formulated T1 and T2 before I throw the big O in. So, like I did over here, I created some sort of function. So I have these two things here. One for linear search, one for binary search. Now remember, I alluded to that there can be possible implementations of linear search on a computer. And there also could be implementations of binary search on a computer. And where each one of those constants that we derived can be CPU cycles on the actual computer. So I just want to motivate this with one last picture before we switch to a new topic. So here's the picture. So this is how so I ultimately want to answer our question. How do I know one algorithm is more efficient than another for all the problem instances over the entire thing, in the worst case? I'm going to draw two circles. These are going to represent these two sets that I have here. So this inner bubble is going to have functions like log n in it. Might have some other functions in here. The point is it has t2 of n in here. So this right here is this bubble here, the circle. This is the set known as big O of log n. Outside this bubble, there could be more functions out here. You can have n, for example. Then t1 of n is sitting out here. However, this larger bubble is the set big O of n. Now I want you to notice that our functions for binary search, they're sitting inside this innermost bubble. The ones for linear search are sitting outside this bubble, but they're inside big O of n. This is what I meant the other day, by the way, when I talked about containment, like saying subset. So this is a proper subset of big O of n. Now, so these are the time complexities laid out in terms of sets. So I'm going to say T2 of n is the running time. So you're going to see why I don't really care about the actual measured time. I care about these steps dictated by the machine model. Here we go. This is the big cherry on top. T2 of n is the running time of every implementation of binary search. We can say binary search is more efficient than linear search. For our problem, right? Remember, this is the search problem where I have the array that's sorted. We can say definitively, when we talk about in terms of the machine model, that binary search is more efficient than linear search in the worst case. So this is very interesting in its own right. So remember, every one of these implementations will have different constants that I can calculate when I do, say I did an exact analysis. Where I count up all the lines and I compute some formula that represents the total amount of time. Each machine will have different constants. The point is now I have a way of talking about all possible computers that can be modeled after the RAM model. And each one of these has different constants. But now I have a way of saying, okay, well, there might be some point n where one algorithm is going to all of a sudden do much better. So I'm going to be splicing these two things together, and that's why the big O notation is very useful. It is a way we can capture all the problem instances in one kind of nugget to talk about the algorithm's complexity without too many redundancies. The point is that now I have some mathematical way of saying, hey, look, this is the efficiency of this algorithm, and now I can compare two algorithms, at least in a mathematically formal way. Now, I must give this with interesting caveats because some people might be looking at this and saying, okay, well, Dan, there could be always a possibility that you could be ignoring certain instances of a certain size, like where n is like 10 or something. Like say if I give you a really small array, maybe linear search might be better. Or maybe some sorting algorithms. If I consider sorting, bubble sort actually works pretty well with very small length arrays. That is actually a true statement. However, that is not what we're actually trying to do here. We're trying to capture over all the entire problem instances. Remember, that's an infinite collection of problem instances. So in terms of practice, you still need to consider maybe particular sizes of n, but this is a much more broader way and more mathematically fundamental way of talking about algorithm analysis, if you see what I mean. So I'm not talking about particular implementations of a particular size. I'm talking about, I give you this algorithm, I want to determine its complexity, I want some way of telling you that this algorithm is more efficient than that algorithm. And the whole picture I want to put for you is that we're going to use this RAM model for our analysis. Now, if you find that this machine model is too loosey-goosey, you can always make the model more particular, where maybe you might consider multiplications more special than just addition. Likewise, there might be certain things you might take a little bit more aggressively over other things. But you'll find that this RAM model tends to be pretty standard. It's pretty common in the literature, and we'll be using it throughout the class. So hopefully this gives you the nice picture of where we're going with things. So the reason why we say binary search is more efficient is because it's in big O of log n. It technically is also in big O of n. However, linear search is only in big O of n, but not in big O of log n. Okay? Is that neat? So, I'm going to spend the last maybe few minutes encouraging another problem for us. So this concludes our main discussion on analysis of algorithms. So this should be setting up most of the framework for which we're going to talk about algorithms in this class. We'll see lots of examples. So if you're asking, well, Dan, I didn't really quite get how you counted up those instructions, that's okay. We're going to see a lot of examples how we do this. But don't hesitate to ask me questions. I'm very happy to answer these kind of things. So I'm going to spend this last bit of time on dictionaries. So we're going to be switching topics. We're going to talk about dictionaries. So this is going to be one of the fundamental ADTs we're going to talk about in this class a lot. So this is going to be cast as the dictionary problem. So remember how I said that data structures can almost be viewed like problems, because I gave you some ADT, your job is to implement all of its operations. So you have to provide a bunch of algorithms, each one for one of your operations for the ADT, and how you organize the data matters. So I'm just going to introduce what the dictionary is, and then we'll come back to this next day, okay? So dictionaries model a searchable collection of records where each record is of the form key, value, or data. So there's pairs, i.e. a pair, key, comma, value. So it's an ordered pair. So I should mention that this collection is so-called dynamic in the sense that you can add and remove records from the dictionary. As the name suggests, you gotta imagine this like a dictionary or a phone book or a database of a bunch of records where each record has a key. This key is unique, meaning there's no duplicates. So I'll say multiple records with the same key are not allowed. So no duplicate keys, okay? But they can have the same value. So two records can have the same value, but they just can't have the same key, okay? So those are the main rules. So you're gonna imagine this like the following. So here's some natural ways of viewing this in terms of applications. You're gonna understand that dictionaries are just all over the place. Student record database. So that's a good example. So imagine I have a bunch of student records and some database. So you're gonna find dictionaries and databases tend to go hand in hand. A lot of the fundamental operations of a database are dictionaries. So if I look at a database, a lot of the main ideas behind it or how we query data from it typically takes the form of what we're going to talk about here, an ADT called a dictionary. A lot of them are variants of this. And another one is an address book. So I can imagine I have a book. So here's a picture of a book. I promise no pretty pictures. This book is melting in the microwave, by the way. There's my dictionary. It's kind of melting like a s'more over a roasted fire. Don't do that to your dictionary, okay? You need to use it to look up words sometimes. So you gotta imagine this like a dictionary where you get records from the dictionary. You maybe add things to the dictionary. You put them in. Or you might remove records from the dictionary. So I'm just going to write down the definition of a dictionary, ADT, and then we're going to stop for today. And we'll talk more about dictionaries next class. So I need to emphasize that this is going to be a core data structures related problem we're going to see throughout the rest of this class for a good chunk of it. So very important you know what a dictionary is. Dictionary ADT. A dictionary D is a set of records / items each with a key and value or data. I'll just use those as synonyms very often when we talk about this. Dictionary D has the following operations. So I'm going to write down the first three main ones, and then I'll leave the last ones to look for in the notes, because there's about 5 other ones. But I'll write them up next time, some of these other ones, and I'll quickly gloss over them. But I'm going to talk about the 3 main ones that we'll focus on. So the first one is called get, and it has one parameter, which is going to be the key. If D has an entry with key K, return its associated value. Otherwise, running out of space on the right. Otherwise, return null. So I query for a key. So I query a key with a key. You return back me the value that's stored at that record. If it doesn't exist, you just return null. Seems pretty intuitive. Put, you give me a key and a value. Insert record. You're going to insert the record, which is a pair, KV, into D, if K is in D already, return error. So in something like Java, this would be an exception you're going to throw. So remember, we cannot have records with duplicate keys. That is something forbidden in our ADT. The last of these three is remove. The name's very intuitive. If D has a record with key K, remove it from D, and return its value. Now, if you don't find the key, so that record with the key, when you try to remove, you're going to say otherwise return error. So if the key doesn't exist and you try to delete it, return error. Quite simple. So this is what the dictionary ADT, these are the three primary operations. We're going to look at a lot of these algorithms for implementing these with various data structures. And we're going to see, I'm going to mention those other ones next day, but I'll only kind of gloss over them, okay? So that being said, we're going to stop here for today. I want to say thank you very much for your patience and have yourself a beautiful day. I'll see you later.